Another example, this is a simply supported beam again. So we've got a pin connection at one end. That's what this little symbol represents. I should really have explained that a long time ago. And this is a roller connection. That's what that little symbol represents. And it's got a line load on it. So for every meter along this beam, we're adding a load of 2 kilonewtons. So for each meter along, there's 2 kilonewtons, which is maybe 200 kilograms, 200 kilograms. So not too big a load. So 2 kilonewtons per meter along that beam. And so we're trying to find the free body diagram this time when we've got a UDL. A UDL. It's uniformly distributed, this one. A line load. Excuse me. So the first thing we do is find the reactions again. This one's a bit easy because it's symmetrical. So we've only got a vertical force. It's 2 kilonewtons per meter over 6 meters. So altogether you've got 12 kilonewtons. It's the area under the line load, remember, is the magnitude of the force. And then, because it's symmetrical, that must be split evenly between the two supports. So we've got 6 kilonewtons per side. If it had been a more complicated problem, we would have looked at figuring out the equivalent point load. We would have figured out equivalent point load and drawn that in the free body diagram without the UDL. And maybe it wouldn't be in, so if it was a triangular load, so let me just do a very rubbish sketch over here. So you might have had a triangular load of something like that. And well, that's a trapezoidal load, but whatever. And then you'd have replaced that with the equivalent point load, which maybe would have been a bit more to this side, and then you'd have used the usual rules for equilibrium. Some of the x components is 0, some of the y components is 0, and some of the moments is 0 to find those two reactions. But then you have to remember, if you do all that, when you come back to looking at sections again, you have to go back to applying the UDL, don't forget that. And then you figure out the equivalent point load for just the UDL just on one side. Okay, so this, changing it to an equivalent point load for the whole thing, that works fine as long as you're getting the external reactions. But you can't use that same force once you start looking at internal forces, because obviously there's load on this side. If you were to take a section here and you've just used this force, all of this load's disappeared, so that's going to change the internal forces here. Anyway, for this case it's dead easy, it's symmetrical, so we must have the same load on each side and they must add up to the total load and be in the opposite direction, therefore there's 6 kilonewtons each side. So what happens when you've got this kind of line load? So this is like a smeared out load, and you're just spreading this load out in a line across this. Remember we talked about you can visualize this by thinking of stacking bricks. And so this would be, all the bricks would be the same height, so you might be 3 or 4 bricks high, and you've got this big block of bricks. Go back if you can't remember that, go and look at it again. So let's have a look at what happens with the sections first, and then we'll try and figure out a quicker way just to draw the free body diagram when you have got a line load like this. So we've taken a section just 1 meter from, I haven't really given these names, but we could say 1 meter, well, let's just say 1 meter from the left-hand side. 1 meter from the left-hand side. Now this is the point where you have to be careful about signs. It's a bit different. We're only thinking about shear at the moment. In fact, there might be an axial, there isn't in this one, because there's no x components of forces and a moment, and then you'd have a shear as well. Excuse me. And so when we're drawing on that shear, we're always thinking about what is positive shear. Well, positive shear is when it deforms the beam this way. So it's up on the left, down on the right, and so our shear is going down the way like that. Then we're using the usual rules. So we want to make sure the sum of the y components is 0 for shear. And so we're going to have up 6 kilonewtons, which is fine. So we've got up 6 kilonewtons. Then we've got to figure out what to do with the with this line load. Well, this is where you've drawn the line load for that part, for that half, or for that segment that's on the left-hand side of where you've cut the beam. And so we'd find the equivalent point load just for that little bit. And the magnitude's in the center because it's a rectangular loading, so it's in the center. Excuse me. And the magnitude is just the area under this, so it'd be 2 times 1, so it's the area under the UDL. 2 times 1, so it would be 2 kilonewtons. And then we'd have a shear going down the way, so we get a positive shear deformation. And if it turns out to be negative, that means it's negative shear. Therefore, and this is V, whatever, what are we going to call this? V1 for 1 meter. And so you could do the whole summing thing. So sum of the y components is 0, therefore up 6. Oh, we've got that 2 kilonewtons. And then minus 2, sort everything out, all the minus 2 kilonewtons, because it's kilonewtons per meter. So minus 2 kilonewtons, and then VA is also, this V1 is also downwards, minus V1 equals 0. So therefore, don't really know why I put the units in, minus 2 minus V1, take the V1 to the other side. So, and then this is 6 minus 2 is 4, so V1 is going to be 4 kilonewtons. So the shear is 4 kilonewtons when we've come along 1 meter. Now at the start, this is just a point load, so we can use the normal rule, just follow the load. And so if we go across to the graph here, our first point has gone up 6 kilonewtons, so it would be here. By the time we get 1 meter along, we have gone down to 4 kilonewton shear, okay, because this 2 kilonewtons per meter, so we're losing 2 kilonewtons every meter we go along, so it's 2 kilonewtons, therefore V1 is equal to 4. And we can just take a shortcut, rather than doing all this, we can just say V1 is equal to the sum of these forces. So for the next one, the equivalent point load this time would be 2 kilonewtons per meter, 2 meters long, so therefore the equivalent point load would be 4 kilonewtons. It's rectangular, so it's in the middle. And we'd have V2, so V2 this time. And if we go through all this again, we'll find out that V2 is equal to 6 minus 4, which is equal to 2 kilonewtons. And that makes sense. So you're saying I'm putting a load on of 2 kilonewtons per meter. And so I started off at 6 kilonewtons shear. This is going across the way. So every time, it's almost like following the load. And so we've gone 1 meter, so it's dropped by 2 kilonewtons, because it's 2 kilonewtons per meter. We go another meter, it'll drop by another 2 kilonewtons. And so the shear at this point is going to be 2 kilonewtons. If we go along another meter, this time the point load would be again in the center, and this is going to be 2 kilonewtons, 3 meters, so it's 2 kilonewtons per meter over 3 meters, so that's going to be 6 kilonewtons this time. And so we're going up 6, down, up 6 kilonewtons, down 6 kilonewtons. So by the time you get to this point, your V, this is V3 this time, is 6 minus 6, which is equal to 0 kilonewtons. So we'll add another point. So now we've got to 0 shear. And we could keep going. I haven't rubbed that out very well. So if we went along to 4 meters, this time we'd have 2 kilonewtons per meter, 4 meters long. Something that's okay. Just I haven't put it in a very nice spot. And so this time, this would be 8 kilonewtons would be the equivalent point load, just the area under the line load, or the area under the UDL in this case, because it's uniform. And so this time, the way I'm doing all these in different colors, this time V at 4 meters would be 6 take away 8, which is going to be minus 2 kilonewtons. And so the next point is going to be down here. And you can see that for every meter we go along, we're going to drop another 2 kilonewtons, because it's 2 kilonewtons per meter. And so just without doing the sections, we can figure out it would be like that. And it would work for all the points in between. And so the load is just, or the change in the shear force is just the same as the change in the load, and the load is just, oops, gone too far, it's just the line load times the distance you've travelled. And so you can imagine that we could figure out for all the points in between, and we'd find it would end up being just a straight line like that as the shape of our shear force diagram. What I'm going to do, I'll leave those on so people know what we've done. And then what's going to happen is we're going to get to the other end of this, we're going to get to here, and we're going to have a 6 kilonewton force upwards. And so we just follow that, the same as we did when it was just point loads. And so we go 6 kilonewtons upwards, which takes us back to 0, which means that we've probably got the right answer. Then you wouldn't usually draw those points, but then you would just shade that in. So the trick here ends up being the magnitude of the line load. If you take the negative of that, it's the gradient of this line. And so this is going down. So if you've got 2 kilonewtons, well, actually it's the right direction. This is going down the way. This is going down the way. And so the magnitude of this force is 2 kilonewtons per meters downwards. And we can see that what happens to our shear force diagram, it just drops by 2 kilonewtons per meter down the way. So it's basically following this UDL. So if that had been, let's just try and draw it on. So if that had only been 1 kilonewton per meter, you'd have ended up getting half the reactions, because you'd have just had 1 times 6, which would have been 6. And so each side would have been 3, and you would have ended up with a shear force diagram more like that. So it would only drop 1 kilonewton for every meter it went along. Okay, so that's what you do with UDLs. So you just think about it in terms of, look, this is 2 kilonewtons per meter downwards, and therefore my shear must drop by 2 kilonewtons per meter must drop by 2 kilonewtons for every meter I travel. And because this is all spread out, it ends up being a straight line. And that saves you having to go through all these calculations for the actual section. Yeah, I think that'll do that. Okay, so now we'll go on and try and put some of this together. I don't think for this course we're not going to go beyond UDLs, because that gets complicated enough with bending moment diagrams. And by the time you get, so we could have a look at, triangular loadings. So triangular line loads, but when you start getting into triangular line loads and so on, it helps to have a fair bit of maths, which some people in the class don't have. And so we're not going to get onto those. But the rules are similar. It's not too hard to figure it out. And if you're going on to do Mech-Eng, it would be worth having a look at this. So it's in the textbooks. So it'd be worth having a look at that so that you can carry it on into your studies in coming years in Mech-Eng.